Yes, good morning all of you. Very good morning. Last class our discussion was about the characteristics of charge. Discussed the properties such as quantization of charge, additive properties of the charge, conservation of the charge, and also the expulsion property of the charge. In fact, we said it is the expulsion property of charge exhibited by conductors when a conductor is charged, either positive or negative. Either case. What is meant by charging a conductor also we have discussed it. So one more time I remind you, since the time has come, that conductor when loses its electrons, the free electrons, then what happens? It acquires excess positive charge. Losing of electrons acquires excess positive charge. So now all that positive charge will be present only on the surface. It is as if all the charges are pushed by some agency and they reach the surface and reside only on the surface. Similarly, if the conductor is given excess of electrons, the conductor gaining electrons, we may get some doubts how this gain or loss of electron. Let us not go into those details now. Let us take only the final case of gain, what happens, loss of electrons, what happens. So gain of electrons by the conductor, it acquires excess negative charge that also appears on the surface, and all these charges, they show the tendency of leaving the surface as well. And therefore whenever a conductor is charged, because of this expulsion property, all the charges now residing on the surface, they also exhibit one extra pressure. They tend to move away from the surface as well. So this will cause an extra outward pressure. Now today let us see some of the examples of understanding this expulsion property of charge. Whenever we write any expression, the understanding of the symbols and how to relate that equation to a given physical situation. So let me show two examples here. Now yesterday it was the case that because of the expulsion property, only surface charge distribution possible for conductors. Volume charge distribution never occurs for conductor, such that sigma is Q by A, which you find sigma proportional to 1 by A for surface area. So more surface area, lesser sigma is one such result. When we consider such surfaces, at least for our board examinations, seat examinations, we have more cases of spherical surfaces. So for spherical surfaces of radius capital R, I will write this expression as Q by 4 pi r square. You remember that R is the radius of the spherical surface, 4 pi r square is its surface area. Now remember, this I am writing for a specific case of spherical surfaces. So once again here you will see that sigma and radius, they are inversely related. Now when we are talking about spherical surfaces, remember this is again a 5-star point I am telling you, which will make use very frequently in all our physics topics. Supposing when you consider two spherical surfaces. See, this is one spherical surface I have shown, and suppose this is another spherical surface. What we find is that now we say this is more curved, degree of curvature is more. We say this is less curved, degree of curvature is lesser. Now two things are important, whether it is asked about degree of curvature or radius of curvature is an important thing. Now here, let me take this as A and let me take this as B. Now it comes to degree of curvature. Please look at this carefully. Degree of curvature comparison, what do you write? Degree of curvature of A is less than that of B. With respect to I am talking degree of curvature. Whereas if it is a radius of curvature, if we are comparing, what is that you find? A happens to be a bigger, this part becomes bigger sphere and this part forms a smaller sphere, is it not? Therefore, now with respect to radius of curvature, we will write R A greater than or B or. So always remember, degree of curvature and radius of curvature are inversely related. Now in our case, this sigma, the surface charge density, is always inversely proportional to surface area. Inversely proportional to surface area means directly proportional to degree of curvature. Such will be the case. Now, because of this, I would like to give you one example. Say sigma proportional to 1 by A. Suppose I have a surface, a spherical surface. This is a uniform surface, you can see, right? Because spherical surface, the surface is uniform throughout, because if you consider any point on the surface, the radius of curvature will be the same, small r, capital R, A, whatever symbol that we use. Same radius of curvature. Therefore, when such spherical surfaces or spherical bodies, spherical conductors are charged, in this case, sigma is constant, sigma is uniform. Uniform distribution of charge will be the case. Whenever we consider uniform, need not be spherical always. Any shape where we find that uniformity of the surface, the distribution of charge is also uniform. Sigma same. Whereas, let me see another example. I am now showing another surface, some arbitrary shape. Some arbitrary shape. Suppose here it is like this. An object like this, it's a surface. Then in such case, what do we observe? What do we observe? Suppose it is like this. This surface will find that, see, look at this part. This part is more curved. Highest curvature we will find here. Is it a degree of curvature I am talking about? This is highest degree of curvature, and this part or some other parcels, you look at this part. This part we will find less curvature, more radius of curvature. Therefore, now when this kind of conductor of arbitrary shape, it is charged, then it is not uniform distribution of charge. Charge gets distributed non-uniformly such that, see, more curvature, I am talking about degree of curvature, no confusions. More curved surfaces which appears to be sharper and more radius of curvature appears to be blunt. Therefore, here when we consider this is the most curved path, it will have more or higher surface charge density, and here at this part it will be the lesser or the least surface charge density, and depending upon the degree of curvature at other places also sigma varies. So this is one such important case to remember. When a conductor is charged, sigma surface charge density may be uniform or may be non-uniform depending upon the nature of surface. Now we make use of such one property. What is the property? We all know that in the rainy season it's a common observation to all of us. We observe these lightnings. Lightning is nothing but the electricity with respect to atmosphere. So lightning when it happens, huge charges will now transfer from clouds to earth. That is what is called as lightning. When such lightning falls on any building or any other things, it makes a lot of damage. And to avoid such damages, to minimize such damages, lightning rods are used. Right? Lightning rods is again one such principle, one such device based on this principle. Now when it is the case of lightning rods, did you ever see these lightning rods? Lightning rods will have sharp edges. They will have very sharp edges like this. Supposing I just made a rod which I have very sharp edges, and you can just imagine it as a trishul. Very sharp edges are now seen. It is not blunt. It is very having sharp edges. Why lightning rods are made with sharp edges? It can be a 2-mark question or sometimes a CET assertion reasoning question. So lightning rods with sharp edges for this reason, sigma proportional to 1 by A, because these sharp edges will absorb or will acquire more and more charge. If it is blunt, it will receive or it can accumulate or it can accumulate only very small amount of charges. For that reason, lightning rods have sharp edges. Similarly, expulsion of charge, we said a property. Look at one more example. It is said that, it can be a 2-mark question again. What is that question? So bubble is charged. Supposing it is positively charged sometimes so told, or it is charged negatively other times told. If soap bubble is charged, what happens to its size is the question. Now we know about this soap bubble already in our first PU surface tension property. We have find out the excess pressure inside the bubble. All these things are there. Now I just can't go back and discuss all those things at present. We'll discuss this in some other part when we meet in person. Now you see, when it is the soap bubble, it is charged, suppose positively charged. Soap bubble is charged positively. According to this expulsion property, we showed that all these charges, they create extra outward pressure. What is the meaning of outward pressure? Outward pressure means it tends to increase the size. Inward pressure always tends to decrease the pressure. Therefore, this excess charge on the surface, extra outward pressure, therefore the size always increases. Can be positively charged or negatively charged. The size of the soap bubble always increases when it is charged. So that is what is the property of expulsion. Now we are discussing one more, last but not least, one more important characteristic of the charge, the invariance of charge. What is meant by this invariance? We have a principle called the general theory of relativity proposed by Einstein, where there is one particular concept of relativistic effect. What is meant by relativistic effect? Any particle, when moving at a speed comparable to speed of light, I said comparable to speed of light, then some very interesting changes will occur. So interesting that according to Newtonian mechanics, mass, the length, which is the size, and time are called as fundamental quantities, and they do not depend upon any physical quantity. They are called fundamental quantities. But that idea is blown off by the relativity concept by Einstein. When particle moves at a speed comparable to speed of light, which is very high, because speed of light itself is 3 into 10 raised 8 meter per second. To know the meaning of that number, it is 3 lakh kilometers in 1 second. Unbelievably high velocity. Now the point is that even velocity is comparable to speed of light should be at least of the order of 10 raised 5 meter per second. So velocities of the order of 10 power 5 meter per second or more, then such effects will happen which are called as relativistic effects, such that as velocity increases, mass increases. Remember, as velocity of the particle increases, mass of the particle increases. But contrary to that, size of the particle will decrease. And also there is a relation corresponding to time as well, that is called as time dilation. Let us discuss at some other part. Now I am discussing only about two things. What is that? Mass increases, size decreases, time also changes. But what about the charge? Supposing we consider a particle like proton and it is made to move at a very high speed, then this is what is the statement that we are making. Invariance of charge. Charge on a particle on a particle has no relativistic effect. See here, I am telling you no, capitals, underlining, no relativistic effect. No relativistic effect. Again, now we can give a statement. Earlier we thought mass is the fundamental quantity. Mass is not a fundamental quantity. It undergoes relativist effect. In fact, charge is the most fundamental quantity of the matter, one can say, because it is not changing even with respect to relativistic effects. No change. Therefore, now here I am writing that Q dynamic, when the particle is in motion, again as I told you, those speeds very high comparable to speed of light. Q dynamic, the charge on the particle when it is in motion, is equal to charge on the particle when it is at rest, static. So this is what is the property of invariance of charge. No relativistic effect on charge on the particle. Now one more time, one 2 marks question is asked like this. When electron or proton, any charged particle, when a charged particle is accelerated through to high speeds, what happens to its specific charge is the question. Right? What is the question? Charged particle accelerated to very high speeds, what happens to specific charge? Now what is meant by specific charge? If Q is the charge of the particle and M is its mass, then we write Q by M as specific charge. Q by M is specific charge of the particle. Now you see, this is the question asked not with respect to the charge or mass, but with respect to the specific charge. Now what is your answer? Due to relativistic effect, right? Due to relativistic effect. Suppose if Q by M becomes Q dash upon M dash. Remember here, due to relativistic effect, earlier discussion you substitute Q dash is equal to Q. Q dash is equal to Q and M dash is less than M. M dash is less than M. What is happening? No change in the numerator, but denominator is decreasing. Therefore, Q dash by M dash is greater than Q by M. Specific charge of the particle is increasing when it is accelerated to very high velocities, is the answer. And here, the mentioning of this relativistic effect, what happens? Q dash is equal to Q, M dash less than M. Q dash is equal to Q, M dash less than M, and hence the result specific charge decreases. So these are our properties of charges, right? Quantization, conservation, additive property, expulsion property of the charge, and the invariance property of charge. Now let us come to the other topics which are very trivial. I just make a small mention of that before we get into all important big topic, big concept of our entire electrostatics. Electrostatics, the name itself suggests that we are discussing about the properties or behavior of the charges at rest, static electrostatics. We never discuss any property or behavior of the charges in these particular discussions. That will be another subject matter, becomes current electricity. Now, our next important title is methods of charging a conductor. Methods of charging a conductor, which is called as electrification. Now that earlier we have given small principles about the modern theory of electrons, according to which we have said what do we mean by conductor, what do we mean by insulator, what is meant by quantization, what is meant by excess positive charge, what is meant by excess negative charge. Now, when it comes to the methods of charging, we will list some three names. First one is by friction. Charging by friction. Now when one of the methods, the earlier methods by which we can find this charging is charging by friction. Charging by friction. A very one line or two line explanation I would like to give. Earlier we have taken the case a glass rod, plastic rod, rubbed with fur material, silk material, wool material like that. Now that when two objects are rubbed with each other, is a kind of interaction between them, remember. In this process of rubbing, what happens? One body loses electrons, so gains excess positive charge. So whatever electrons are lost by one will be gained by the other, and that will acquire excess negative charge. Therefore, in the process of friction, what is happening? Yes, exactly, material transfer of electrons is happening. If electrons are transferred from A to B and the transfer happened due to this friction and all, A acquires positive charge and B acquires negative charge. So this is by friction. There is transfer of electrons from one body to another body. Now you see, the second one we are mentioning here as methods of charging is by conduction. C-O-N-D-U-C-T-I-O-N, conduction method. In this conduction method, now you see, here, this is a conductor which is uncharged conductor. To begin with, there is no excess charge. Always remember, charge on a body, that statement never refers to the total charge inside the body. No, it only refers to excess of positive or excess of negative charge. Initially it is uncharged. Now here we brought another material, say another conductor, and this is positively charged. This is positively charged, and what I did is I brought it into the contact. This is A and this is B. Initially A without charge, B with charge, and there is physical contact between A and B. All such physical contact whenever happens, again physical transfer of electrons happen, such that now A also acquires, this is the picture that we are in. Suppose initially this is Q1 that is equal to 0, and suppose this is Q2 greater than 0. Now the case that comes would be like this. Here A acquires some positive charge and there is positive charge on the B as well. Now two or three important things, let us have a good understanding. What is that? Now here this charge is suppose Q1 dash, alright, Q1 becomes Q1 dash. After touching, this is Q2 becomes Q2 dash. Now we observe that in this case, earlier friction, transfer of electrons happen, and one acquires positive charge, the other acquires negative charge there. But now here you see, when it is the conduction, physical contact between two, the nature of the charge will be same on both of them due to contact. That the conduction is what is the meaning of that. So now both acquire like charges such that Q1 dash is now greater than 0 and Q2 dash is less than Q2. This charge magnitude will decrease because some of the charge is now it has conducted given to this conductor A. Therefore, whenever we see such case of two conductors coming into contact, before contact whatever may be the charges on those surfaces, but after touching both will acquire like charge. I am telling you, not same charge, no, they acquire like charge, like both positive or both negative. Now the numbers may be different. Again here comes your one more doubt, sir. Is it possible that this Q1 dash and Q2 dash, the charges after touching, whether they are equal or unequal, which is more will be the question. See, that's a very interesting question, and answer for that would be, Now in this case, Q1 dash is equal to Q2 dash. Yes, it is possible when these conditions like A1 is equal to A2. What does it mean? Surface areas of A and B if same, irrespective of size and the uniform distribution, please take that. Then A1 is equal to A2, we have Q1 dash is equal to Q2 dash. That is the possibility. So depending upon the areas, we have different possibilities, equal, unequal. In that unequal also, whether A acquires more or B acquires more. These things we will come across in our next topics. Whether Q1 dash is more or Q2 dash is more, we will also do such examples also. But here you remember only the principle, what are the possibilities. The possibilities are, they can be equal or they can be unequal. Now it is another method, induction method, charging by induction, INDU CTION, right? Okay, induction. In this case, there is no physical contact between the bodies or the conductors that we are talking about. Now here you see, supposing I have a copper sphere and everything, this is an insulating rod. All these things I am marking, these are insulating material, does not acquire any charge. So whatever we talk about charge, it will be only on this sphere that we have shown. Supposing it is given a positive charge. You may wonder why always I talk about positive charge, sir. Can we talk with negative charge? Yes, you can do. To be positive in our attitude, I am showing positive charge, right? So this is a positively charged sphere. Again, is it always the shape of a sphere? No, any arbitrary shape. Figure looks good like this. Your textbook has given this one and I am also using the same. Now this is A and this is another copper sphere, whether same size or different size, it doesn't matter. This is another copper sphere B, which is initially isolated such that the charge on this is QB is equal to 0, uncharged sphere. Now the point is that when they are brought closer, A brought closer to B. In earlier cases of friction method and also conduction method, we have seen the physical transfer of those free electrons from one to the other. Whereas here, it is not brought into contact. They are only brought closer to each other. Then what happens? And it will be, you imagine both are very, very close to each other. Okay. Close to each other. It is brought. A brought closer to B. Then what happens, this property comes into play. That is what we now call, naming it as induction. Now this positive charge present, we know that unlike charges attracts. Therefore, this positive charge, what it does is start attracting the free electrons which are present on the surface of B, right? There are free electrons on the surface. They start experiencing attraction due to this positive charge. Therefore, now the tendency is that all the electrons, they show a tendency of moving towards A. All the electrons from this end to this end, as if they migrate, such things happen. So this end, all the electrons will now appear. Earlier there were free electrons in distribution such that net charge was 0 at any place. But now this kind of migration due to attraction experienced by this positive charge, electrons now appear. Here the lack of electron situation will be there. Therefore we call that as plus. So what is happening? Charged conductor brought near uncharged conductor. Then the nearer face, the nearer surface acquires unlike charge, and the farther side, the rarer side acquires the like charge. See, positive Farther also getting positive. So farther side, F-A-R-T-H-E-R, not farther. Farther side it is acquiring like charge, nearer side it is acquiring negative charge. Now this is not due to the transfer of electrons from A to B, rather it is redistribution of the free electrons on the surface of B. See, by the property of induction, we can give one more statement, an important statement in electrostatics. What is that? In our earlier discussion, you remember, A was charged and B was uncharged to begin with. That was the case. Now, due to this method of induction, the phenomena of induction, now it is acquiring this negative charge, nearer side, farther side, like charge, right? Unlike charge, like charge. Because of this, now A starts attracting B. Is it not? A starts attracting B because of this induction, which tells us that a charged conductor can attract another unlike charged conductor, or even it can attract uncharged conductor also. Repeat my statement. A charged conductor can attract another unlikely charged conductor. Also it can attract uncharged conductor also. Therefore now the question is that if a conductor A I have and another conductor B I have, such that it is initially charged. A is a charged conductor and we don't know about the state of the B, whether it is charged or uncharged, we don't know. Now the question is, when A is brought near B, if it attracts, what is the inference about the B? Whether you say B is charged or B is uncharged, what are the different possibilities is the question. Right, now you see, when A is brought near B, supposing B is also charged but unlike case 1 I am writing, suppose B is also in the state of charging such that it has negative charge. B has negative charge, first possibility, then certainly A attracts B. What is the other case? Suppose B is uncharged state, there is no excess charge on B, then also what happens? A brought near B, the phenomena of induction, the nearer side acquiring unlike charge. Then also A attracts B. So a charged conductor attracting another conductor, we can never say the state of the charge on the second object. That is, attraction is not a sure test to state about the electric charge property because of the property of induction. Therefore, repulsion is the sure test of the state of charging, but not attraction is another point that we can give because of this property of induction. See, all these are very trivial things. Only I wanted to mention the three names like the conduction, the induction and the friction methods. Now comes all important biggest topic of our complete electrostatics. Now let us see what is the biggest topic. Hope you understood all the characteristics of the charges with good details. Now let us come to that core point of the unit. Not just core point of the first unit of electrostatics. In fact, this will be the core for the entire electrostatics. The electrostatic force. Earlier we have mentioned that the charges exert forces on each other such that like charges repel and unlike charges attract. Now comes the all important law in electrostatics. How to evaluate the force between the charges, and that is what is the famous Coulomb's inverse square law. Now please take a good look at the situation and each and every statement that we now give. Now, Coulomb's inverse square. See here, Q1, and this is another charge Q2. Now Q1 and Q2 are two stationary point charges. So in the very beginning you will find an important point. Coulombic force is applicable for number 1, point charges. Number 2, it is applicable for stationary, that is the charges at rest. Now this is the line joining I am showing. The line joining the two charges. This is the line joining the two charges, such that the distance between the two charges, I do it with a symbol small r. Distance between the two charges. Now there are two forces, F12 bar. F12 bar, what is the meaning of that? This is force on Q1 due to Q2. See, look at this symbol, F12 bar, it means force on Q1 due to Q2. And similarly, this F21 bar, another force, that is the force on Q2 due to Q1. Force on Q2, force on Q1. The symbols F12 bar and F21 bar, they form action-reaction pair. And we know that for every case of action-reaction, the magnitudes are same. Magnitudes are same. If now here I am now writing it as mod F12 bar is same as mod F21 bar, and that is what I take it as capital F. Now let me explain the situation just briefly one more time. Q1 and Q2 stationary point charges at a distance r. Then Q1 and Q2 exert force on each other such that F12 bar force on Q1 due to Q2, or F21 bar is force on Q2 due to Q1, the action-reaction pair. And of course, as we know, it can be either attractive force or repulsive force depending upon the nature of charges. Because of this action-reaction pair, the magnitudes are same. Now here comes the Coulomb's law. The Coulomb's law says that according to Coulomb's law, see, I am just making a notes like this. It will be a straightforward notes for you for board examination as well. According to Coulomb's law, now this force which we have taken it as F, which is the magnitude of both F12 bar and F12 bar, F proportional to Q1, Q2. Remember, F proportional to Q1, no. F proportional to Q2, no. F is proportional to Q1, Q2, the product of the charges. And the second result, of course, through all very extensive observation, this is the case. F proportional to 1 by R square. If R is the distance between the two charges, look at this character. Force inversely proportional to not distance but square of the distance, hence it is called as inverse square law. Coulomb's law is inverse square law because of this relation of force and distance. Now we combine these two equations and we write it as F proportional to Q1 Q2 by R square. And we know that any proportionality will write it as an equality by introducing the constant terms. Therefore here we write it as F is equal to, we are now introducing the constant as 1 by 4 pi epsilon naught. Look at this constant that we have represented, 1 upon 4 pi epsilon naught times, of course, Q1 Q2 upon R square. Q1 Q2 by R square. Now let us first talk about this constant. We have this famous expression which is the basics of entire electrostatics. Even in our next chapters like Unit 2, Unit 3 also, this is what is our fundamental to find or to evaluate any other characteristic with respect to the charges. So this, now here 1 by 4 pi epsilon naught we have taken, right? This epsilon naught value, this epsilon naught value is what is called as permittivity, P-E-R-M-I-T-T-I-V-I-T-Y, permittivity of air or vacuum. So what does it mean? Now when we have considered the two charges stationary Q1 and Q2 separated by distance r, there is a medium between the two charges which is going to be vital. Now according to us, here we have shown two charges Q1 and Q2 separated in either air or vacuum. This expression 1 by 4 pi epsilon naught Q1 Q2 by r square is applicable only, yes, for the charges in air. Now we also get it out. Supposing if it is not air but other medium, yes, we will come to that point also. Now let us first see what is this electrostatic force between the charges in air. So remember this expression only for charges in air. This epsilon naught permittivity of air, this permittivity of air or vacuum, a universal constant. Remember this is a universal constant and the value is evaluated by Cavendish experiment, right? There is one experiment, Cavendish's experiment. That Cavendish experiment gives the value of epsilon naught as 8.85 2 decimals into 10 rise minus 12, 10 rise minus 12. Now here comes the unit. That is what earlier I have told you. I can just mention the unit straight away, but it is of no use. You only do that. Suppose you take this epsilon naught this side, F you write it here, right? Then what is that expression? Numerator you have charge into charge square, that is Coulomb square. Numerator you have force, which becomes Newton, and the numerator you have also distance square, that is meter square. Therefore numerator is Coulomb square and the denominator is Newton meter square. Coulomb square by Newton meter square is the SI unit of epsilon naught. So this is the expression for electrostatic force between charges in air. Now let us see the case. Suppose other than air, if we have a different medium between the two charges, then let us have it. This 1 by 4 pi epsilon Q1 Q2 by r square in A, we have given the value of epsilon naught. Also remember, we should give the value of 1 by 4 pi epsilon naught also. See, this 1 by 4 pi epsilon naught, I will write it as small k. Look at the symbol carefully, because every time we don't write 1 by 4 pi epsilon naught, simply I write it small k, which means 1 by 4 pi epsilon naught, and the magnitude is 9 into 10 raised 9. The value of 1 by 4 pi epsilon naught is 9 into 10 raised 9. So this will help us in quick answers of any simplifications for this electrostatic force. Remember, here we are writing the force only in the scalar form, that is we are writing the magnitude of the force. We are not doing it in the vector form, which we will do afterwards. So this is Coulombic force in scalar form, that too in air. Now comes, supposing other than air, if there is any other medium, that medium can be either conducting medium or dielectric medium. You remember these words? we have defined conductors and insulators, which are otherwise called as dielectrics. So supposing if the space is other than A, then we are writing this expression as, see here. Now I will write it as F dash, the new force other than A, such that, remember, now both Q1 and Q2, the entire space between Q1 and Q2 is filled with the medium. Not partially some space between Q1 and Q2, we are not writing such case. Now we are writing Q1 and Q2, and the entire space between Q1 and Q2 is filled with a medium other than A. Then F dash is 1 upon 4 pi epsilon naught times capital K. See, capital K. Don't confuse with this one. I have taken small k as 9 into 10 raised 9, which is 1 by 4 pi epsilon naught whole. Whereas here now I am writing capital K times the same Q1 Q2 by R square. This is in medium. This is in medium other than vacuum or A. Now what is the difference that you found? The difference between the two F and F dash, air and medium, is, look at this denominator term, 4 pi epsilon naught. Here it is 4 pi epsilon naught times capital K. What is that capital K? Now here we introduce one more new parameter. What is that? K for, see this K, capital K is what is called as dielectric constant. Dielectric constant, otherwise also called as, the same K can also be used with the symbol epsilon R. Earlier we have used the epsilon naught, permittivity of air or vacuum. So epsilon R is relative permittivity. Permittivity, relative permittivity, and such that how we define this epsilon R, such that, see, either K the same as epsilon R, both are the same, and in all the next topics I will be making use of the symbol K rather than epsilon R. You can use any of your choice. Epsilon R is equal to epsilon by epsilon naught. Epsilon by epsilon naught. We know about this epsilon naught. What is that? Permittivity. Now, let us say add one more sentence. Permittivity of vacuum, air, right? Now we will get a question. What is meant by this permittivity? See, permittivity is a characteristic of medium with respect to electricity, which we will understand in a better way in the next 1 or 2 sessions, because in between we have to speak about many other things. Afterwards, when the right time comes, I will explain you what do you mean by this permittivity. So now generally permittivity is one of the characteristics of the medium with respect to electricity. Now vacuum has permittivity. Similarly, any other medium will also have its own permittivity, which we have taken as epsilon. So epsilon is permittivity of medium, epsilon naught permittivity of vacuum. So this is permittivity of medium. You can see it is the ratio of same quantity, numerator, denominator with same units. Therefore, epsilon R is unitless, no units and no dimensions also. And one more important point about K. Many things are to be told. I will just add 1 or 2. We shall come to other things in the latter stage. Now the most important point is K is always greater than 1 for any medium. Remember? For any medium, whether it is insulated, dielectric medium or it is conducting medium, K always greater than 1 such that for conductors like metals, for conductors the value of K is infinite. This is an important point to be remembered. 1 mark question, 2 mark question. K is infinite. K infinite for conducting mediums such as metals. K is infinite. Therefore now when you look at those two expressions of F and F dash, the difference, as you can see, the denominator term dielectric constant. Therefore what do you observe here? Since K is always greater than 1, I can now say that F dash, the force between two charges in a medium, is always less than force between two charges in A. So the force between two charges depends upon the medium between the two charges such that it is always maximum in air or vacuum, and it is always lesser when we introduce a medium between the two charges. Now this is about the Coulombic force in its scalar form. Much is to be discussed now with respect to its vector nature and also the characteristics of this Coulombic force. Discussion, what did you understand? Epsilon naught is a universal constant. Number is given with units 8.85, 10 raised minus 12 Coulomb square per Newton meter square. Whereas epsilon, permittivity of medium, epsilon r, relative permittivity of the medium, they are different for different medium. See this expression, if I say epsilon, I can write it as epsilon naught times epsilon r, which is otherwise capital K. K is always greater than 1 we said, therefore this epsilon always greater than epsilon naught. These are the important things that you have to take. Epsilon greater than epsilon naught, because K is always greater than 1, epsilon r value greater than 1. Therefore now I have said that K value is infinite for conductors. Supposing a 1 mark question asked you in the board examination, what is the value of dielectric constant for A? For A, epsilon becomes epsilon naught for epsilon r is equal to 1. So this is how our idea should expand through observation. Supposing if this is the case, what are the possibilities? Or other than this, what are the possibilities? So K is infinite for metals, the conductors, whereas K value is 1 for vacuum, or even for air also, we can take the value of K as 1. Now also look at one more time, look at those expressions F dash and F. What is the only difference that you find? This 1 by 4 plus Q1 Q2 by R square is there in F dash also. The only difference is this denominator term, capital K. Therefore, from those two equations we can say this is what is F dash, the force between charges in medium, equal to the force between the charges in A by capital K epsilon r value, which is always greater than 1. Earlier statement is there. Therefore now look at these two, F dash in the medium, F in the air for the same setup of the charges. Therefore now you will observe that F dash is less than F. F dash is less than F. Force between the charges is maximum in air or vacuum. For any other medium, force is decreasing. Force is decreasing such that supposing now you have it out. Supposing the entire medium between Q1 and Q2 filled with a metal, a conducting medium, then what happens? We said K is infinity. So K put value infinity, then F dash is equal to 0 you get. Is it not? Therefore now I will write F dash is equal to 0 is also possible. What is meant by F dash is equal to 0? That means that the force between the two charges will be ceased, will be stopped. There is no interaction between them when the entire space between them is filled with that metal, the conducting medium. F dash is equal to 0 is also a possibility. This is an important expression for 1 mark, 2 marks, problems as well. Because here again you will find 1, 2, 3 terms. Force in A, force in the medium and directly constant. Keywords. Keywords. Force in the medium. Force in the A, directly constant. Any 2 parameters given and third one asked. If you have this kind of observation, you can only create number of 1 marks and 2 marks questions. Because in the board examination, they are going to be very critical in the scoring of that 69 or 70. All those essay questions and other things, it's cup of tea for everyone. Whereas, when it comes to 1 marks and 2 marks, you should have an idea what should be your method of using the class notebook. Because that will contain many questions and answers. And I hope your observation skills improve on every day basis and every week basis.